Now, welcome to the last part of today's lecture and the last part of the deep learning analysis in general of the lecture series. What we're going to do now is we are planning to analyze osteoarthritis with deep learning and simply apply networks on that problem. Now, how do we get started with that big task? Well, at first we need some packages. There are very nice and very important packages that we can use. They're based on PyTorch. It is a really famous deep learning framework by Facebook. And we are going to use on top of that framework, which is called fast.ai. It's really handy. It's simple to use. It gives us a lot of very compliant functions that we can then use for our problems and get started really fast, as the name suggests. So what else do we need? We need to install all this. We just use this task in our command line and get everything rolling. Now, I won't go into too much detail to get those things started. You can simply look on the repository websites to get going with that. Often, if you're going on Colab, this will be done for you very simply by simply applying this task. So what else do we need? We can simply start our program and see, okay, we can run this. We have a new version of FastAI, which is 2.25, so that everything seems to be fine so far. The next thing we need is a data set. Well, you heard in the previous lecture that maintaining data sets is a task on its own. So we won't go into too much detail about this, just so that you know, it is a long task and it takes a long hours to get this thing in a proper environment working. However, there are a lot of free data sets that we can simply go and use. For example, the osteoarthritis data set, we can simply go along this link and download the whole thing. And the only thing we have to remember for today is where we save those things. So here for my task, I have it here. Everything is stored in this repository, and I have the path which points towards this repository. So I need that too. Good. And now we can get started with deep learning. We have a data set. We want to apply a network on it, and we want to improve our predictions. So before we can really get rolling with training networks, first we have to get our architecture really to be set up. Now, how does that work? Well, FastAI gives us a lot of very handy functionality in order to supply us with the relevant parts that we need. So what's going to happen basically is we're going to use the information we see here in that repository. We're going to see we have a test, a train and validation data, etc. And we want to design a training scenario where we have some kind of logic which is capable of loading pictures from the training set and knows which labels are applied to those pictures. And then it will load them. Then it will perform training with a neural network. And in the end, we can go on the validation set and improve or see how good we are. So in order to get that running with FastAI, there is a very nice API called Application Programming Interface again. It's the data block. So this data block requires us to do certain things we first have to understand. And once we get those running, we can then design our training building on top of that. So if you look at the code that just comes from the documentation of FastAI, the data block demands certain things. Well, at first it wants to know what kind of blocks we're going to be using, because everything is constructed in some kind of blocks in here. So we're going to be using image data. So we're going to have an image block, and we're going to assign each of those images to a category. So the one other thing is a category block. That's just a very general structure we're defining. The reason we're doing is that we're capable of then transforming everything into different scenarios whenever we want it. For example, if we want to do segmentation, or if we want to do natural language processing, that can be changed very simple and easily, building from this block API. That's why we're using this. So we, in our case, have an image block and a category block, so we know that. And now we have a lot of things we have to do, because we need to get our item somehow. We need a function which gets all the images we need. We have to get a label for those images. We have to somehow split between training and validation data. Then another thing, item transforms, this one stands for item transforms, this part just means that all the items you maintain, all the images you get, they have to fit within some kind of uniform boundaries. So let's say you have images which are 224 times 224, but sometimes you have larger images or smaller ones. You should maintain a certain standard within those. So it's very profitable to keep the same size in order for the network to work at all. That's why we're going to apply item transforms as well. And the last thing we're going to be looking at for the data block are the batch transformations. So they're going to be more or less describing what are we going to do with each training batch. So we're going to pick out some images, we're going to send them to the network. Are we going to apply some augmentations to them? Are we going to rotate them or something? That's going to be within the batch transforms. So there are a lot of functions that need to be defined, and we have to define them. That's a very important part before we can really get to train networks. And then this data block has a really simple function of applying data loaders on it, you call that, and you give it the actual path you're using, and everything will be in a proper format. So you will have a data loader, and this data loader will then provide your network with training data or validation data. Okay, so we need those 5 functions first, and then we can get moving onward. So how do we get all those items? How do we get all the images from the dataset? Well, we already defined, so we have everything stored here in this folder, and we have the path pointing to that folder, so that shouldn't be too difficult, right? Well, there is a good function already pre-designed for us from FastAI, which is simply get image files. So this one will just provide us with all the strings of each image file within that whole repository. And every time you're like confused, okay, what does this function actually do? You can always get a cell, you can go double question mark, and you type in the function you require, and you see some kind of implementation that is within here. So it will go through all folders and pick up each image it finds in them. So very simple function. So we get this big list of strings with all image files. We can see this one is 9,786, has so many elements. So this is a large list we have here. So this is going to be the more or less the access to our image. Now we have to somehow define as the next step to get the Y, the label we actually want. So a very simple way of maintaining a label is if you look at the path that we have, for example, here for one image, you can see that the label is hidden within the path name already. Because if you look here, that's somehow the image ID. And before that, it's stored in the folder 0, because in the folder 0 are all images of the category 0. So how can we do that? We can write our own function, which gets the whole file name, and then we call it in a path, get the parent. So that would be all this. And then we get the name of the last one that's right here. So that will define our label. And always when we write functions down. This is just a very simple function. Okay, how do I get from this path? How do I get the label 0 out of it? We have to test it. Does 0 come out of this? Yes. Okay, that looks good already. So we get all the file names, we get the labels. Now we have to somehow split, because we have training and validation data. So we can see here, if we look again at the top view of the repository, we can see that everything is split into models. We're not gonna need that, but we're gonna have test, train, and val. So train for training data and val for validation data. So we have to somehow tell the model here, or the data block, that this is split according to this logic. To get this done, there is another very handy function that is already provided to us. We can see it here in the documentation. So just jump there, and you have a lot of splitters you can use. You can go by indexes, you can apply many more that are explained here, or you can just use randomness. In order to compare, however, in this data set, we already have something predefined for us. By this logic here, it's defined by test, train, and validation. So we are simply gonna go for that architecture as well. So what we're gonna do is we're gonna use this grandparent splitter. If we don't understand what it's doing, we can also see up some documentation for it. It's gonna pick up simply the architecture or the storage numbers and from the parent and then the grandparent. So we're going to look at this one. So this is Autotest. We're not going to look at this in more detail, but this is going to be similar to test train on top of here. So this one is going to pick that and compare it to the names it is given. So here we have to pay a bit of attention, because in our repository it's called test, train, and val. However, the function in general expects to have train and valid as the names it has to be looking for in order to split the data. So we have to give him that information. Train name stays the same. We could omit that. However, for the whole, to complete everything, we're going to write it down, and the valid name has to be changed from valid to val. So that looks good now. We can omit that and use this new splitter for our data block. So we have again the items, we have the labels. Now we have a splitter. The next thing we're going to need are the transforms. We want to transform all our images on the same size. So in order to do this, there is also a very handy function. We want to have everything on the same size. So there's that resize function. It's going to pick up all the images and resize them to the new size that we define. Well, the images should already be at the size of 224, but just to be sure, we're gonna apply this operator here. So to make sure all the images have the same size and we can properly train. Okay, so we have all this. The only thing missing now is some kind of augmentation. In order to get any of those networks to properly train, it is necessary to apply some kind of augmentations. Very useful augmentations in that case are simply mirroring. Horizontally often is very practical. So a left knee and a right knee, actually, they represent the same problem. We can rotate and everything is fine, or mirror. Then rotate is also very nice, because often the scans aren't on the perfect plane. They are a bit rotated around. So we try to further emphasize this variation on the data sets by rotating on our own. Or we can scale up the image or scale it down a bit. All this can be done with those transforms, and finding the perfect parameters for those transformations is a long process and takes an awful lot of time. So that's something very handy here too, because we're giving a function that's called augmented transforms, and it has the best practices of current neural network research. for us. So we can see here what are good parameters. For example, 10 degrees is a good option. Zoom, you don't go smaller, but you increase the size a bit. You change the lightnings, warping, etc. So there are many, many parameters that have to be defined, those hyperparameters for training, and we're given all those parameters already and a very good approximation for our problem. So we shouldn't rework that too much. We simply are happy that we can take all these advantages for us. So our transforms are simply going to be those augmented transforms. We have to pay attention here that we apply the size we want as well. So in this type, that would be the 224. We're going to use that size for the transforms. And that's it. So we have gone through that in a rather fast manner. If you ever have to train those neural networks, I really recommend you start using with this software with FastAI. And if you have any questions, you can go back to the steps that you saw, and you have your own data set. So you have to define your own function, how to maintain the file names, how to get the label from it, how to split them according to train and validation data, how to get all the files you have on the same page, so on the same size in that case, and then how to apply proper transformations on this. Now, once you have that, you can define your data loader. That is the one being responsible for training in the end. So once we have defined the data block, it's very easy to get that data loader. You simply call the data loader function. You give it the path that he is going to have to search for. So that's the main path we have defined at the start. Then the next very important thing we should be talking about is the batch size, here shortened as BS. The batch size defines how many images at once are we going to load into the network. And this is going to change training, because as we've discussed in lecture before, there are some kind of normalizations like batch norm. So those are going to be averaging over the whole batch, and things get more stable once that batch is large. So that's nice. Why not define a very, very large batch size like 256 or something? There are often potentials of 2. Well, why don't we just get it as large as possible? The problem is that often we are limited with our computational capacity. Our GPU unit has limited storage, and therefore we have to compensate this. We have to find a compromise between storage capability and normalization and batch norm precisions. So a general good compromise is to be around 64. A batch size of 64 is something good to get started. If you're going to use larger models, there will be often an error occurring to you where it says CUDA out of memory error. And the simple fix you're going to use there is simply go ahead to that batch size. Remember that, oh, memory error, that's the batch size, and decrease it, half it, for example. Then you're going to solve that problem, and you can go working with larger and larger models. Then something a bit unfortunate for Windows is that these data loaders are capable of parallelizing CPU calculations, which is really nice. It makes everything super, super fast. However, that only works for Linux. So on a Windows PC, you have to add this line here that the number of workers is 0. That means it's actually 1. However, things will start working only if you set that to 0 for the Windows PC. If you are on a server on Google Colab, on Linux, you can ignore that line and everything will be faster, just to mention that. And then the most important things, once you get everything set up, you have the data block, you have the data loader, you want to see what's going on. So the most important thing is to then show the batch. How does it look like? What do we see? Well, now we see, okay, we have these images of the knee, and they seem to be some kind of augmentation on them. I'm going to just demonstrate it by removing the augmentations first. So this looks much more clean. Everything is very straight. There are no rotations. It has about the same lightning. You can see each image is has its own label. That's a 0, this is a 1, 2, etc. So that everything that looks to be nice already. So let's get those transformations back on in order to get proper training running, and we can see we have more variance now within our batch. Good. That's it for data block. That's a very important part. Remember to go back to this step once you should ever need a network to train on your own. You can always go there, check the steps out and modify them for your own needs. Now to the real business, let's get our neural networks. So we have image data. Which kind of networks are we going to use? We're going to use convolutional neural networks. Again, now it could get really frustrating and really a lot of work, but FastAI supplies us with an awesome tool set of convolutional neural networks that we can simply use. So there's the function of CNN learner. We give it our data loaders. Then we define some kind of model we want. For example, this is a ResNet with 50 layers, and we define some kind of metrics that we're going to evaluate this model on. So that would be the accuracy, for example. So let's simply get that thing running, and that's something German still in here. Let's just look at what is all in this network. We can see we have a new loss function and cross entropy loss we're going to be using because we are looking at categorical data. That's the perfect loss function for this. And we can even print out some kind of summary of that network, which will give us all the layers and the operations that we're going to apply. So convolutions, batch norming, ReLU, max pool, all those expressions are appearing here again. This is what a neural network, a convolutional neural network is composed of, and we can see all that being applied in here. So that's a very long summary of that whole network. So let's ignore that for a second, not see it all the time. And basically what's happening here is we've made the 50-layer component of a residual neural network. So that's the same thing as we saw here. Okay, we have the data loaders, we have the network. Now we can finally perform training. So there are many options for starting training in here. I'm going to again show the best practices of training. A very good function that we can use that is already given to us, predefined to us, is the fit one cycle function, which will do the following. It will go for as many epochs as we want. So in this case, that would be a 4. For 4 epochs, we will train the whole data set, the whole training data set. And we're going to have a learning rate which will at first increase a bit and then decrease. So that's a very good practice, that you start with a very low learning rate to get things started and somehow get things moving into a right direction. Once you know you got the direction more or less stable, then you can increase the learning rate, so you will have faster training, and in the end you want to specialize, so you will reduce again. So that's the one cycle procedure. We're going to use simple 4 training phases here. You can see here I already did that. For each cycle it takes a bit of time. Unfortunately, this is only on my laptop, so this could work on your laptops too. It's nothing too crazy that is demanded here. So again, I want to save those 4 minutes of waiting, and we can see our accuracy starts at about 40% and increases to, let's see, 55% for start. So we're already, well, okay, we're already somewhere making progress. So after we have trained anything, we want to see how good are we actually. We want to again look at the inputs, look at the outputs of what our network does. So there are very nice functions for this. We can simply, for example, go to show results. So we can see where everything could work out. If it's green, we see, okay, it was already doing these ones correctly, but there are still many red ones, so it misjudged the class of all these images. So we're not really there yet. We have somehow got started, but it's not really precise. How precise is it though? In order to really give this term some value, we have another really handy function. It is the classification interpretation. So we're gonna analyze the validation data set again and see what has actually happened here. And we can plot these two things here. These are the confusion matrix. I'm going to show it in a second. And then the classification report. We first see here the classification report. So for each class, we have the precision, the recall, and other scores. So this is already gives you a very good overview. If you're a data scientist, you can look at all these numbers, all these metrics, and they're directly there, and you can see if you have improved or not. A very visual example of those interpretations is the confusion matrix, to really see where did things go wrong. It is just a matrix. However, it has some really nice understanding to it. Let's try to get it in one image. Here we go. So it shows what the network predicted and what the values actually were. And what we can see from this is that it tends to overpredict the class 0. There are a lot of predictions in the 0 phase, although there were actually maybe 3s, 2s, 1s, and of course also 0s. And the second class is also over-predicted. You can see that here. There are many predictions on that one. So that really gives you a better feeling of what is actually going wrong right now. We're having an over-prediction of class 0 and class 2. Okay. So how can we improve this? Well, there are many, many ways to improve that. However, I want to show some further very interesting improvement strategies. This is, for example, the learning rate finder. So what this does is it will try to keep training upon the current state of the network. So what we did up here is what we always do after training. We save what we have. So for example, this was trial 1. Here we saved it, and then we can load that trial 1 and evaluate how good it was. And now we can pick up from that trial 1 and then perform some kind of learning rate finding. So that will be really high specialized on which learning rate should we actually choose for improved training, for keeping on training from here onward. And it will deliver us some kind of idea of where we should get this training to go on and to improve further. So this is not, to be honest, the best example of the learning rate finder. Usually you want a bit clearer surface of it. So it should rather be like it has a top and then it decreases before, if the learning rate gets too high, it increases again. So this actually looks like it's stuck a bit on a local minima, and it doesn't really find a good way out of there. So that's why it's really flat down here. However, we get an idea that maybe around 10-4, the training seems to be at least stable. It doesn't explode, so it doesn't get unstable. So we can use this learning rate as a good starting approximation for further training. So what we did here is simply get the neural network to continue its work. We give it this new learning rate, and we save it as the second trial. So 40 epochs, then takes a bit longer, so 40 minutes roundabout, and we succeed at around 62%. Again, we can load this new training procedure and interpret what is going on. So see precision, recall, F1 score. And we have a similar problem, yet not as strong as before. Again, looking at the confusion matrix, you directly can see what's going on. It's still an overrepresentation of class 0 and 2. However, we see that we also have improved because we have made less mistakes with class 3 here those are reduced and we make less mistakes with class 0 compared to before. So we can really see some kind of difference how certain images have been moved to a better prediction and are now more or less within the right trajectory. So we can see this is a much better approach than we have previously seen. However, this is not at all finished here because this is a very basic approach we took. We simply trained a bit more, and then we stopped. However, we didn't touch any kind of transformations or anything. So there's a lot of potential in getting that network to be much better than it is right now. Just as a comparison, we end up at around 62%, 61% here of accuracy, and the current state of the art is about 70% that they achieved. So already this is not too far off, and we have just gotten started. We just trained 2 networks and didn't really perform any kind of parameter optimization. So those 70% are perfectly beatable with this kind of setup. We can use a larger network, etc. So I would suggest that it's your time to get this to improve. If you want to write a new publication, if you want to go and beat the current state of the art in osteoarthritis diagnosis, then go pick up from here, write your own network, vary the augmentation, make the network larger, use some kind of new training techniques like mixed precision or mix up, and always save what you have, validate what you have, and maybe also go in the direction of a larger batch size to get this thing better and better. And yeah, so please go ahead. This can be a really fun task. You can always see your small improvements on it. And I think it is definitely beatable in this case. So maybe if anybody of you has time for a new publication, go ahead and try to beat the current standard. So that's all for today. I hope you have some idea now of how you can get started, where to look things up, what is required for training. And yeah, thank you for your attention, and please check out the FastAI libraries because they have much better explanations than I can provide you. And yeah, they have awesome tutorials, so check out their work, please. Thank you.